So, welcome everyone, and hello if you just recently joined. We are actually close to the end of this conference, this great conference, and it feels a little bit like having now the main acts on the stage, like on a concert. So, one of these main acts is Thomas, and it's my distinct pleasure to introduce Thomas Liedtke, who is not only a friend of mine, but also my longtime mentor of all things cybersecurity. So Thomas Liedtke is manager consulting at Vector Consulting Services. He is member of the National Dean AK Cybersecurity, but also member of the Intax Advisory Board. People dealing with ASPICE know what I'm talking about. He studied computer science and mathematics at University of Stuttgart, and above all, he is a Tara expert who will share insights on how to derive cybersecurity requirements on different levels of the V model with the help of the Tara methods. Thomas, the stage is yours.
Thank you, Sergey, for the kind introduction. So I would like to introduce in my presentation for us evening. Title is End-to-End Derivation of Cybersecurity Requirements at Different Levels of a V Model Using Tara Methods. A colleague of mine, Richard Messnertz, coming from Intax, and myself, we sat together and we thought about how can we show the Tara end-to-end in a V model on different levels. We have a lot of experiences by reviewing Taras, by assessing the MEN 7 or the clause 15 of the 21434. And this is what about I will talking about. And therefore, thank you for the invitation to the Secure Our Street 2023 conference. I will start with introduction, some words for the motivation, and then I will talk about the system level, the software level, and as both can come together, and then a short summary on that. All of you, I suppose you know the clause 15 of the ISO SAE 21434. We have a general method can be invoked from different points in the life cycle, so on different levels can be invoked from system level, software, hardware, whatever. Can be even started with a vulnerability or weakness to assess it. First time, typically it's during the concept phase. So after the item definition is there, you need some cybersecurity goals in order to derive cybersecurity controls and requirements. And therefore, first time you will perform the Tara, you will start with the asset identification, the enumeration, cybersecurity property assignment, and the identification of the damage scenarios on that. The next step then will be to determine the impact rating and to think about the threat scenarios, to identify the threat scenarios, and then to think about what kind of attacks, what attack paths can trigger the threat scenario, that can realize the threat scenario, and then think about how easy it will be to perform the attack path in order for a successful exploitation of vulnerability, for instance. Both together, the impact rating and the attack feasibility rating will lead to the determination of risk value, and at the end, between 1 and 5, you have a risk value. Then you can think about how to treat the risk, and you can choose one of the 4 options to treat the risk. You will come back to the clause 9 then, and then you will think about the risk treatment option, and in cases you want to reduce a risk, for instance, you will select the cybersecurity control. You can, after specifying the cybersecurity goal, think about the control, the requirements, and so on. You can derive them and go for the model like for our requirements as well. For the cybersecurity requirements, you can have on system level, you can have on software level, hardware level. At the very beginning of a project, after item definition, perhaps you don't know about some specific details of your software, and therefore you keep on the system level, but at the end you will see you have to put both together. Having a look on one example. So I will talk about a lock command for steering. So that means that you cannot steer anymore, that if you park your vehicle, you will have a lock command in the steering wheel so that it is locked. And on a very high level on cybersecurity goal, the cybersecurity goal could be, if you want to protect the asset, a lock command received by the steering ECU The cybersecurity goal could be steering lock shall not react or work triggered by a malicious lock command. That could be your cybersecurity goal. You want to protect that, and you want to avoid that your steering lock will be lock the steering if the command is not valid for this. On the next level, on a system level, you can think about what requirements can be realized the cybersecurity goal. What kind of cybersecurity controls you need in order to achieve the cybersecurity goal. First one could be the authentication. So it means the log command shall be authenticated as one cybersecurity control. Another one can be non-repudiation. That means you cannot perform a replay attack, for instance. So non-repudiation of log command shall be ensured by logging received log commands. That means you will observe that this command was already performed. So it's a replay attack. You will not react anymore. That are the requirements on a system level. On the next level, on a software and hardware level, you could derive further. For instance, one software requirement could be use the CSM and MAC verify function of the cryptographic service manager library to verify the authenticity of received log command. That means on software level, you will provide the authentication and the requirement that it will verify the authenticity. On hardware, you can do the same one. That means you have a HSM module with a secure flash memory, for instance, and this shall be used to store the private key material for message authentication. For the authentication, you need a private key, and this is stored in an HSM. So this is the level, and you see how it is going down. And most of the TARAs we saw in the past so far, they were using the stride threat modeling model in order to derive the threat or the kind of threats. If you have a cybersecurity property, so in the original stride literature, it's named as security attribute or attack pattern. You see, for instance, authentication, imitation of something or someone different, the integrity, non-repudiation, confidentiality, availability, and authorization. The standard itself, it's requiring for the three ones for CIA. In most of the TARAs we saw, it is extended to the 6 ones. Why? Because then it is more easier to derive the threat for it. For instance, for the authentication, spoofing will be the stride threat modeling. So it means attackers pretend to be someone or something else. Spoofing, it's the direct one-to-one link to authentication. For integrity, it's tampering. That means nothing can be maliciously tampered. For non-repudiation, it's repudiation. For the confidentiality, the threat will be information disclosure. And for the availability, it will be denial of service. And last but not least, if you want to protect authorization, then you can hamper the threat of elevation of privilege. So it means if you once defined the assets and you have once assigned the cybersecurity properties to your assets to be protected, then you can easily, more or less easily, derive what kind of threats can compromise your asset, can violate the asset or the cybersecurity property. Let's have a look on a system level. How is a TARA performed on a system level? We see frequently that it is more or less function oriented. That means an OEM, for instance, the main interest of the OEM is that the functions will work as specified. Therefore, you can have the assets and an enumeration of all the functions. They have to protect it. It's frequently focused only on the high-level threats. It's so to avoid that you will get lost in detail. If you have all the individual CAN signals already on that level, you will not be able to complete the TARA successfully. Sometimes you can use a pre-filter mechanism. For instance, if an OEM says, you don't have to take care about remote attacks, I will take care about, so please consider only attacks coming from the OBD, for instance. That could be a pre-filtered mechanism as a hint, as an assumption for a tier 1 or for an OEM that he says, I do not take care about all the possible attacks and threats on that level already. Pay attention about the assumption. if you have some assumptions or considerations, you have to specify a claim in order to validate it at the end, because otherwise, like for safety, if you have some assumption in the very beginning as input for a HA, you have to make sure that the assumptions can be validated later on and they are not going wrong. You have to consider the UNICE Annex 5 on a high level already, because this is part of the UNICE homologation. The UNICE Annex 5 is providing some threat catalogs as mandatorily to be considered to avoid that someone is making it too easy, the game saying, I have only considered one threat family, the others I don't care, or I don't even do not know, and then I'm ready with the Tara. So this is a basic level that you have to consider at least the threat families mentioned in the UNICE Annex 5. And there's a table B and C for the measurement and for the measures that you have to consider some proposed measures already on that level. The modeling assessment is useful for the design, but of course can never guarantee secure implementation. Next one, the selection of cybersecurity controls and derivation of cybersecurity requirements using architectural vulnerability analysis. Very important point. This is something that security projects are different from, let's say, normal project or from a safety project. You need, this is a requirement of the 2034 as well, you need a specific vulnerability and weakness analysis of your architecture. This you can do only if you have a view on your architecture. Automotive Spice, for instance, is supporting you, because if you remember on SWE2 or a SYS2 process, you know you have to create a system architecture, and RSpice already is asking you for different views you have to provide. This is supporting your Tara because you will see the attack vectors in that system architecture. You see all the interfaces and you see the attack surface you have to take into account for your Tara. You can identify the asset. We will see in a picture how this could be done for the data and functions, for instance, which could be maliciously modified by corresponding attacks. It's not part so far for the Tara, according to the 2034, that you have to perform iterations. That means you perform it once, the Tara. You have some cybersecurity goals identified, you have selected cybersecurity controls, you have some requirements, you have to show that you will fulfill the requirements, that you will achieve the cybersecurity goals at the end. But there's no evaluation how much the risk is now reduced and it is sufficiently secure now. This is something will come up in edition 2, I suppose, with the target attack feasibility. That means if you have a kind of measure to evaluate it, how secure your product at the end is. Up to now, the Tara does not mandate these iterations, so it's up to you to decide that your cybersecurity controls are effective sufficiently. And last but not least, on that page, the assessment of risk values does not consider existing measures, especially what we see in a lot of projects which are taking care about safety as well. The safety measures are not considered in the Tara. Latest, if you have defined your cybersecurity goal and you are talking about the attack paths, the cybersecurity controls, you have to sit together with the safety domain in order to discuss. Perhaps there are already a lot of safety measures in place which will hamper that the security goal, according to the safety goal, will not or cannot be violated easily by an attack. That means you have to take it into account. Mostly it's the case that it is more difficult to perform the attack because you have to violate and you have to attack the safety measures as well in addition. You have to consider the cybersecurity principles, and there are some principles as an example. The first one, an attack can occur through any interface. Like if you break into a house, typically you have the possibilities of a door and the windows. At Christmas, you have a chimney, but there are only a few possibilities to break into a house. And it's the same here. You need an interface in order to exploit weakness and vulnerability. The asset you can highlight in the architecture, we will see that in an example. And an attack typically is modeled as a chain of event. So there's a scenario, there's a stepwise scenario performed by the attacker in order to create the damage at the end. Along the attack path, this is we will see as well, the countermeasures can be designed very easily if you have the architectural design on that. And you can select out of a pool of possible cybersecurity controls. That means it's not like safety where you need a lot of engineering power and effort to think about how can you make things safe. In security, it's very limited, the possible cybersecurity controls. There are some standards like the NIST SP 800-53 telling you what kinds of possibility in terms of cybersecurity controls you can choose. This is now a picture of our electronic steering column lock item. You see different trust boundaries. So this, for instance, is a trust boundary vehicle, the internal network. Then you have a trust boundary for a vehicle. You have another one, the trust boundary of our ECU. So you have different trust boundaries already there. That means within one trust boundary, you have always the same level of security. You can trust on the errors in the same trust boundary. And you see the interfaces. For instance, you have the mobile phone app, keyless go, or a user, and they can trigger that your steering column lock item will work and will lock the steering. You see the item definition already. You see the operation environment. You see the antenna. You see the gateway server, domain controller, our ECU. You see the motor for locking the steering. And if you want to find an attack, you can think about how is it possible, what are the way to the motor, for instance, of an attacker. Perhaps we'll start with a mobile phone app, and then we will go for the antenna, through the telematics ECU, the gateway server, domain controller, the ECU, and then at the end he will be successful if he can reach the motor to tamper the motor, to tamper configuration data or whatever, how he will destroy the function when it is not working like specified. You see a list of assets. The input commands are assets. The output messages are those one, the mobile phone and apps. The OBD is an asset, and so on. So it means if you have such kind of architecture on your system level, on your item level, then you can identify all the assets you have to protect in order that it is not possible that an attacker, for instance, will perform this attack here. Now you will perform your terror, and this is only an excerpt, so it has many more columns, but this is only the summary at the end. The asset is the function. The asset will be, in case of a lock command, the electronic motor moves a bolt to a locking position of the steering column if validation conditions are valid. Then it should work. This is the specification of a function on that level. The cybersecurity properties, you have the 6 ones I presented before. We decided confidentiality and authorizations are not in the game here, but authentication, integrity, non-repudiation, and availability, we are in the game in the sense of we have to protect, we have to implement something in order to protect authentication, integrity, and so on. You can think about the impact rating. We said the damage will be that at an unintended time, the steering will be locked. And of course, this is a severe safety, financial, and operability impact. For privacy, it has nothing to do with that. Availability, if your steering lock is not available, your car could be stolen, some kind of financial impact, but no safety or operability impact we see on that. The attack feasibility, you have to trust that it is derived according to the attack potential method. At the end, it's a high value means that it is very easy to attack. And you see it according to the threat scenario, spoofed lock command, tampered function, replayed lock command, always lead to the same damage scenario, but the attack is different. So you have 3 different threat scenarios, 3 different attack paths. Some of them are the attack feasibility very low, some of them are high. At the end, if you combine the impact rating and the attack feasibility value, you will get the risk value, a number between 1 and 5. And you see we have some very low, for instance, for privacy, only 1. We have 1 for safety, financial, very high, 5. That is due to the fact that this attack seems to be very easy. So for an attacker, it seems that to attack it with a replayed lock command, this should be the easiest way for him to create the damage. If you have a look on the different attacks, for instance, spoof block command that leads to moving vault at locking position at unintended time. So this is our attack. The attack time is spoofing and it's compromising cybersecurity property authentication. Then you can think about what kind of cybersecurity control we can select. In that case, we are selecting message command authentication and a time span. This is our cybersecurity control we will select in order to protect this asset at the end, and we will avoid that some kind of attacks, the spoofing attacks, can happen successfully. The next one will be tampering for the attack type, and the cybersecurity control will be secure access protocol for UDS, locking of JTAG port, and so on. That means if we know the cybersecurity property, if we know the attack type and the attack, we can select the cybersecurity control accordingly to that. But next, we can combine with the cybersecurity goal that the chain is closed. So the standard let us open how the sequence will be. At the end, you need the complete chain you will see. That means we have a cybersecurity goal 1 in that case. The steering lock unlock shall not react work triggered by a malicious lock unlock command. This is our cybersecurity goal. You remember from our Tara before. The cybersecurity control, now what we have selected in order to achieve the cybersecurity goal is message, command, authentication, and timestamp. We have to think about how can we achieve that, or how can we implement that cybersecurity control, and therefore we need some cybersecurity requirements. This is why we are performing Vitara for, because at the end we are implementing requirements and we want to verify that we can fulfill the requirements in order to get the cybersecurity control implemented and to achieve the cybersecurity goal. In that case, we will derive 2 requirements. The first one, the unlock command shall be authenticated using message authentication code, MAC code, and the second one, the unlock command shall include a freshness counter to avoid replay attacks. So this is our 2 requirements paying to the cybersecurity control message command authentication, and so on. So this is the derivation downwards for V model in order to, at the end, achieve the goals in order to hampering that the threats will be performed. Now we are going down to the software level. On software level, we typically see that Vitara will be performed component-oriented. That means based on a data flow diagram, what you need anyhow, somehow, you need a dynamic view for your architecture on software level. And for the most important components, you can select them as an asset. We will see it in a picture as an example in a few minutes. The threat analysis is performed as a team effort. This is both for software and for system level, of course. We need a system architecture, software and hardware expert, perhaps some auditors, experienced attackers, cybersecurity and security experts. So it's not a thing you can do by your own. You need more people. It's a matter of a team, common team effort activity. That means you need additional views from a cybersecurity point of view, from an architectural point of view, that you can have a look on which cybersecurity controls you will select and what cybersecurity requirements you can derive on that. This you can do based on an architectural vulnerability analysis, for instance. You can assume that you have an HSM already that can support you, or you want to introduce an HSM in order, for instance, to be able to store some private keys, to have some cryptographic algorithms available, and so on, that you have your database of all the functions and services, for instance, your AutoSAR services that you have ready and you can use. Of course, you have to ensure that the integration steps have to be followed. If you have an HSM, if you have an AutoSAR stack, of course, this has to be integrated carefully, and you have to integrate it according to the safety and security manual. Another very important point is that you have typically a state machine in your software, and at the end, you need a specific analysis on architectural level per state. So it's not only used to have one state. Perhaps you will have a secure boot, or you have a boot state session you have a drive session, you have a sleeping mode, whatever. That means you have different states, and for different states, perhaps you need different cybersecurity controls. And therefore, you have to think about you have at least one threat model per session and state, and you have an integrated one if you want to move from one state to another one. This has to be secured as well, because this could be a target from an attacker, but exactly in that state he will attack the system. We will see how the cybersecurity controls can be along the threat models per session and state can be derived, and how the cybersecurity software can be derived based on the cybersecurity controls you have selected. If you are using an AutoSAR, you have a cryptographic service module here, and you have some functions you can use, hash key, MAC authentication, random numbers, and so on. So a lot of them are already there. You don't have to implement it from scratch. You can reuse it if you have a CSM available. Let's have a look on our flow chart, for instance, and this is the drawing how is MS Stride proposing as well. So you have a specific semantic on that, but I think it's easily to understand. So for instance, you have the bus at the very beginning, you have a speed signal, you have a request to lock or unlock the steering board. You have a CAN communication module in there, you have an RTE, where the command will be stored, the speed and the lock request, and then you have a state machine. Depending on the state you are in your architecture, you can decide if you can lock the steering or not. And of course, you have a little bit of safety here as well, because it's a safety goal as well, that the steering will not be locked in an unintended situation. This is a safety as well. So that means there can be already some safety measures implemented here as well. When you have a flash memory, there you will need to configure some data. This is the session concept before your cybersecurity analysis. So very straightforward, 1 to 5, how it is going and how is it working. Automotive spies requires a dynamic design. So this is something you should have anyhow, because this is part of your architectural design. Next, that will be that you will add the analysis of the threats. So you will think about, what about your speed and lock command at the very left side here? So you will have the threat spoofing or the property authentication. That means you want to secure it, that the command has to be authenticated, that spoofing threats are not possible. The same is here on the RTE. If you will store the command, that you think about spoofing and authentication for your both your commands on that. You should think about your ROM memory. The code block could be tampered as well. So there's a property of data integrity. Do you have the correct code block? Was it not tampered before? So all the software and functionality as specified. You will have a state machine. You will have the flash memory for the parking mode limit, for instance. That means if you are driving faster than the parking mode limit, the steering wheel is not allowed to be locked. And this parking mode limit you can store in a flash memory. And of course, somebody could attack this parking mode limit to another higher value. And therefore, you have to avoid the threat of tampering, and you have to protect the data integrity on that. So very straightforward. If you have a first drawing with the straightforward function as the function is working, you can more or less very in a systematic way, you can add the threats and you can add the or assign the cybersecurity properties, and you can think already about the cybersecurity control. And this is coming next. So after that session before, you will add the cybersecurity controls, you will select them. So you will think about, what about the code block, for instance? We said it has to be protected against tampering, so that we can protect the integrity. How can that be done? For instance, you have to signature for the code block, you use that. For the bus, you need some SecOC, the onboard communication in a secure manner, so that you can avoid tamper and integrity to protect here. You can introduce a crypto service manager on that. You can use from a library the make verify start command, the make verify update command, or the make verify finish command on that. So that means this is how you can think about the cybersecurity controls you need in order to protect your cybersecurity properties you have introduced in the picture before. Again, this is a very systematic way forward to identify and select your cybersecurity controls. For all the numbers, you can think about, for instance, parking mode limit. How can you secure that value? Introducing a hash key, for instance, so that the parking mode limit cannot be tampered anymore. This is after adding all your counteractions on that. This is just the explanation of what I said before. So you will find it in the presentation later on or in the PDF. So at the end, what do we received at the end? We have a cybersecurity control in the software architecture, for instance, like authenticate, speed, and lock unlock request, and validate the lock and unlock session on that. You can allocate that, for instance, to the software component session, validation, lock, unlock, and the SecOC. These are your two software components in that case, where you want to implement and realize the requirements. One of the software requirements can then be the first one here, if speed limit parameter is valid and the speed is valid and lock request valid and the speed is less than the speed limit, when you can lock the steering wheel. For the other ones, you have the counter software cybersecurity requirements on that. If the speed limit parameter is invalid or the speed is invalid or the lock request is invalid, when call the safe state. So it means you will not lock, but you will go into the safe state, and so on. So that means in a very systematic manner coming from your cybersecurity control, your allocation to the software component, you can think about how can you realize that at the end you will realize the cybersecurity control. Last but not least, as I said before, you have to think about what about if you will come from one session to another session. And you will have different sessions, like, for instance, a boot session, drive session, and by when are you allowed to go from one session to the other one? Typically, you will have some functional safety startup test, for instance. That means safety has to indicate, yes, you can go now into the drive state. And the same, you have to think about cybersecurity. That means it has to be performed all the checks before if it is allowed to go into a drive session, for instance. That means you have a transition from one state to another one. Your software or your architectural design will tell you what about your states and how are the transitions. That makes the Tara more complicated in the sense of that you have to think about your attacks and you have to think about your threats dependent in what sessions you are. You have to introduce cybersecurity controls differently in a secure boot or in a boot session compared to a drive session, for instance. So it means you have to add this as an additional parameter, as an additional dimension for your Tara, let's say. And at the end, of course, you have to think about what about my transition from one session to the other one, because perhaps it could be an attacker interested in that he will try to attack especially this transition, or that he's able to attack on one session in order to exploit a vulnerability in the next session. So coming to the summary and the recap. So cybersecurity threat analysis and risk assessment have to be performed on several levels. It is not sufficient to have it on one level, on a system level, on a TAR level. Even the standard lets open. He is not forcing you to perform the TAR on different levels. You have to perform it on a high-level system level, typically done by the OEM. Select some cybersecurity controls, some cybersecurity requirements using architectural vulnerability analysis, and the typical boundaries that you will get some cybersecurity requirements already specified by the OEM as a tier 1, but you will typically not have complete access to a TAR completely. What you have to do as a tier 1, you have to perform a TAR on a lower level. for instance, on software level, so that you can have now a detailed look in your ECU. You can perform it component-oriented based on additional views and methods from your architectural design, what you have here. You can use a stride model, which will support you for systematic derivation of the software cybersecurity requirements. Finally, cybersecurity goals, system requirements, and software requirements can be traced for consistency in a systematic way. So if you are familiar with automotive spice, then you know for each level you need to have correctness, completeness, consistency. You have to provide and you have to verify. This you can do with the system as well. So it's more or less the same as ASPICE is requiring anyhow. And this is supporting your procedure for cybersecurity as well. So thank you for listening. Hopefully I had some interesting ideas and I'm excited about your questions.
Thanks, Thomas. So we have around about 8 up to 10 minutes left to address some of the questions we have. The participants already have voted the questions which they like most or want to know the answer to. And I just start from the top. It's a variety of questions, Thomas, so people are very eager to learn about. So the first question would be, which tool do you prefer using to generate Tara reports and to extract requirements, claims, and risk determination?
There are several tools in the market, and it depends a little bit of what the purpose is and how you want to work. I showed some examples based on an Excel tool. You can think about Excel is not very maintainable to create some big attack paths. So there are some other tools where you can perform some attack paths more easily. There are some tools, I do not want to name someone, but there are some tools we have something in between, so you have some tables where you can have a look on it and you can create some attack paths there as well. From my point of view, the most important feature of such kind of tools is that you can have an overview to have a look on consistency. And this, of course, Excel, it's very simple. We easily can verify that all the requirements for clause 15 are fulfilled because you have one line. Automatically, you have the link asset, cybersecurity, property, damage scenario, threat scenario, attack path, and so on. You can see easily how it is, feasibility is rated, how the damage scenario. So this would be a very important point for me, that you have a tool that can, at the end, can show you that all the requirements are fulfilled and give you a good overview. And then typically, you are going into another tool, like, for instance, Enterprise Architect, Polarion, or whatever you have as a requirement management tool that either the goals or latest the requirements you have to copy out of a Tara tool into your requirement management tool. But there's no specific one best tool I know I cannot recommend.
So at least 5 people are now kind of sad that you did not drop some names. But however, that's that's part of the game. So
we can do
thanks.
personal lunch.
Okay, exactly. There will be a possibility to talk with you in the lounge. So maybe join Thomas there, and maybe there are more to ask and more to answer. So the next question. Um, Also interesting, the Tara is leading to the CS goals and selection of particular CS controls later on. What in case if Tara, done on the component level by tier 1, is leading to different cybersecurity goals and controls that the vehicle level Tara done by the OEM? So the interest conflict.
Yes, so and I think it's a typical question which came up we see in the field, because the OEMs normally has some ideas about cybersecurity requirements. That means he will provide some cybersecurity already as an input for you as a tier 1. That means you cannot start by scratch thinking about what are cybersecurity requirements for my project. That means what you are typically doing is you create a Tara on your level, And this is a very complicated thing now to have a look. Is it in contradiction of what you have received already as a cybersecurity requirement by the OEM, or is it part of a requirement? I observe that this is not an easy task, but it could be, of course, you will identify some additional risks, some additional cybersecurity goals you cannot see in the cybersecurity requirements you have got from the OEM. And then, of course, you have to discuss with them when you say, I've performed a terror, I've identified a risk, and I think there are some cybersecurity controls or cybersecurity requirements missing. I have a case, for instance, for one tier one company, they didn't had an HSM on their ECU because up to now they didn't need it. Now we have got a lot of cybersecurity requirements. They have a lot of additional risk identified, and it's not anymore possible for them to implement everything in software. They need an HSM. We have to discuss with the OEM because this is a conflict. Either we want to make it secure when we need more power, we need an HSM, or we cannot implement the security. So my proposal would be discuss it with the OEM. But the OEM anyhow has to have access in your tower. I propose that you tell him what risk you have identified, what cybersecurity controls you have selected, and then to discuss with him.
So, and next and probably last question is the following. Cybersecurity goals must be validated at vehicle level. Is validation of cybersecurity goals at item slash system level and at component level, hardware and software, also mandatory or only recommended or not needed?
I think we had a similar questions in one of the talks before. I say yes. So even the standard is telling you validation is only performed or is performed on vehicle level. As soon as you perform a TARA and you understand the details, that you will be able to specify some cybersecurity goals, then you should be forced to validate them. And I call it validation as well. That means if I start a TARA on software level and I've identified some cybersecurity goals on software level, I have to validate them because validation means I cannot fulfillment. I cannot verify the fulfillment, but I can validate the achievement because I will never have a software secure by 100%. Validation for me means to show a judgment of achievement of a goals. And if you have some goals identified on software level because you have performed TARA on software level, then of course you have to validate it, you have to validate the claims, etc. So therefore, from my point of view, yes, it's mandatory.
Understand. We have like 2 more minutes, and I am that's risky. Let's check if we can give or if you can give a very short answer to that. And it's the following question: should NX5 be examined at the vehicle level or at item level?
Both, I think, because you have to show that you be in line with the Annex 5. If you don't care about Annex 5 and you, on item level, you will only perform a small part of the Annex 5, but the OEM needs your TARA for the homologation because your system has to be homologated at the end, then you will miss something. Beside the fact, at the very beginning of my presentation, I said the example that your OEM is saying you don't have to take care about the threat family because I will take care. But this is something you have to discuss with the OEM, what is done by the vehicle level and what is expected. From my point of view, yes, you have to take into account because in the worst case, your TARA will be shifted to the OEM, shifted to the homologation, to the technical services, and then we will see if there are some if they miss something, then you will not pass the homologation.
Perfect. We are done in time. However, we have still some open questions. So please be everyone invited in the lounge to talk with Thomas directly. Thomas, thank you very much for your
You're welcome.
presentation. See you next time. Bye bye.
Thank you. Bye bye.